a medium, it changes speed and it creates a refracted wave. All right, so remember, we always measure to the normal. Very, 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 very important. There's always the normal. It's a 90-degree line that goes through that barrier. So your angle is measured to the normal, all right? So from the ray to the normal. And then you have your refracted ray, which is your angle of refraction, all right? This one's pretty self-explanatory. Refracted, it's the bent one. And then you have your angle of refraction. This is the one that, just think about, it's where the incident occurs. So initial, there we go. This is another way to think about it, is initial. We've said initial a lot this far this semester. So the initial angle, or the first ray that hits it, all right?
All right.
So then when we look at critical angles, there is a little like round tube with a protractor around it in the back of the room that you can fill up with water. Hopefully you all took some time to pour some water in that and shine the light so that you can see this actually happen. If not, go back to that blue bookshelf and find it. It's like a round thing and it's standing on a stand like this, all right? And you can fill it with water. Fill it to water to that line that goes halfway across it. And you'll see that when you shine light in, it's going to hit right in the middle, and it's going to reflect back down. But it's in water, so why does this happen? Right? If you were to shine it more down here, it's going to go straight through. You're going to see the line come out. All right? But if you, as you move that angle out this way and you hit it at a steeper angle, it's going to reflect straight back down, and you're not going to see it out the top anymore. That is called your critical angle. That angle that you pass, and then all of a sudden it's no longer reflected back through, but when we pass that angle and it reflects down, that is your critical angle. All right, so if you're taking a little thing in the back and you're moving it, and you're moving the laser pointer, and you're going, and it's still showing out. Please be quiet and go. And it's still showing out the top, all right? As you keep moving it, eventually it's gonna stop and you're not gonna see any light come out the top. You have reached the critical angle. Critical meaning it no longer shows through, it can only be reflected. So that is the angle of refraction of 90 degrees, meaning that is the angle of incidence value where your angle is, everything's reflected back into the water, all right? So it is the angle at which everything is reflected. All right, so go do a visual of that and you will see that from the moment it no longer shines through and instead is all reflected back in. All right, so we call that total internal reflection. So once you pass, once you pass that angle, critical angle, and everything is reflected, we call that reflection total internal reflection. Because if this was your round thing in the back, everything is now internally reflected in the water, all right? Internal reflection inside of that water. All right, so total internal reflection is what we call it once we pass the critical angle and everything is reflected into it. Please go in the back and use that tool and see that. This will make 100 times more sense if you can go back there and physically see how that light gets reflected back in. It's like it all of a sudden disappears and shoots down in the inside. It's pretty cool to look at, so please go back there and use that tool and take a look at it. All right, so total internal reflection only takes place when both of the following conditions are met. The light ray has to be starting in the more dense substance, right? What's more dense, water or air? Water. Dense means it's thicker, right? So it has to start in the water and has to be approaching the barrier. It has to be approaching the barrier of a less dense substance, so water to air, all right? And in order to achieve total internal reflection, we have to pass our critical angle, and so our angle has to be greater so that everything is reflected, all right? Before the critical angle, it still shines through. Once we hit the critical angle, everything is reflected. All right, so how do we calculate the critical angle? Your reference table says the sine of the critical angle is N2 over N1, all right? We need to find the angle. We don't want the sine of the angle. That doesn't mean anything to us. We want the angle. So at the very beginning of the year, we talked about some algebraic terms, the opposite, right? What's the opposite of multiply? divide. The opposite of add, subtract. The opposite of square, square root. So what is the opposite of sine? We need to move sine to the other side so that I have the critical angle by itself. The opposite of sine is inverse sine. If you look on your calculators, it is the second sine button, all right? Second S-I-N, and you'll see it comes up with a S-I-N to the -1. All right, so now we've moved the critical angle to the left all by itself so that I can find that angle. All right, so take the inverse sine of both sides, and now you can solve for your angle. All right, so to find at which angle everything's going to be reflected at, you're going to do the inverse sine of the index of refraction of the second substance over the first substance. All right, 1 and 2 should be pretty self-explanatory. All right, look at me. Go color on the paper. All right, 1 and 2 should be pretty self-explanatory. 1 is where the light starts. So this is 1, substance 2 is here. All right, so water would be 1, air would be 2. All right, so the second substance over the first substance. So for instance here, you would look on your reference table. On the front page of your reference table, it says index of refraction, and it lists a ton of different index of refraction values. All right, that's what you need to use to find the N value. All right, the N value comes from the front of your reference table. All right, so you would put the value of air over the value of water for that first example. All right, so let's look at some examples. I don't have that reference table with me, so hopefully they are on the slides here. No, they're not. So let me pull it up. Give me 2 seconds, and I will pull up that chart for you all. All right, I've got my laptop here. Let me find it. All right, so if you see on the front page, I don't know if you all can see this, on the front page of your reference sheet, you should see this. All right, right here is the index of refraction for common substances. All right, so I'm going to use this to kind of go through those that are on the board. No, you don't need to see it, baby. Go color on a piece of paper for me. All right, so let's look at the example. The critical angle for ethanol air. Look. Here we go. Color on your paper here. Here we go. All right. So ethanol air. So we move that sign to the other side. Sign to the -1. And now we need N2 over N1. Very simple. Ethanol is 1, air is 2. So we need air over ethanol. So I'm going to look in our reference table, and the index of refraction for air, that is my coffee, buddy, is 1.00 over the index of refraction for ethanol. All right, ethanol is the same as alcohol. So when you see it say ethanol, ethanol and alcohol are the same. That ends in all. That's an alcohol. All right. So 1.36. Oops. 1.36. So close your parentheses, and if you punch that into your calculator, you should get second sine to the -1. I think this calculator's dead. Second sine to the -1 over 1.36. So if you see, this is what I have in the calculator. Not sure if you all can see this. All right. sine of 1 over 1.36. All right, and then I hit enter, and it tells me that my angle is 0.826 degrees. All right, so 0.826 degrees is my critical angle. Let me make sure we're in the right mode.
Sit, Mommy.
Aha, there we go. My calculator was not in the right mode. It is 47.3 degrees. You should make sure that your calculator is in gradients, so hit mode and make sure it is in gradients. If you can't find it, see if your neighbor can help you find it. That's important. When you are doing wave problems only, it should be in gradients, all right? This is the mode that your calculator needs to be in, is gradients. So 47.3, once I pass a 47-degree angle, my light is now completely reflected back into that same substance. All right, so let's look at another example. Critical angle for flint glass air. So the inverse sine of N2, which is air, over glass. All right, so air was 1.0, and glass, you need to look at flint glass, would be 1.61. All right, so when we plug that in, second sine of 1 divided by 1.61, and I get an angle of 38.4 degrees. All right, that is my critical angle. Once I pass that degrees, now my light is completely reflected back into my same substance. All right, and diamond crown glass, I'll do one more example. Sine to the -1. Crown glass is number 2, diamond is number 1. So the value of crown glass is 1.52 over diamond, which is 2.42. All right, so when I punch that into my calculator, thank you, Ivy, it is 1.52 divided by 2.42. And I get an angle of 38.9 degrees. All right, so that is my angle. All right, that means once I take that light ray and here's my normal. Once I have it at a 38-degree angle, nothing else is going to show out the top. It's all going to reflect back in. So you could calculate the air-water angle and go back and use that tool in the back and see if it matches, and it'll match, all right? So if you were looking at air glass or air water, put air 1 over water, 1.33, all right? And it will calculate the angle at which you should see that laser disappear on that tool in the back of the classroom on the blue bookshelf.
Mommy, help. Mommy.
All right, so let's look at Snell's law. Come here, I'll get it for you. Can you say please? All right, good girl. There you go. You wanted the office pass? Are you going to the office?
Yeah.
Yeah, okay. I don't think that's a good place to go. All right, so Snell's law. This is where a lot of y'all's questions are coming from. So here it is. Snell's law tells me, so for instance, the sunshine is shining onto a surface, all right? So here it says I'm in air, and it's shining into glass, all right? So remember, we have our normal line that goes 90 degrees, all right? Angle of incidence right here, that is the angle at which it hits, and then you have your angle of refraction, which is 25 degrees. So given 3 of these values, I can find the missing one, all right? So you have your N value of that substance and the angle at which it's traveling in. And then you have your N value of the second substance and the angle at which it comes out. So top and bottom. This is all of your ones, all right? Side 1, and the bottom is 2. All right, so you have N1 and an angle 1. You have N2 and an angle 2. So let's look at some examples. Here is your rule. All right, this should be in your reference table. Check and make sure it is in your reference table. And it is your N1 times the sine of angle 1 equals N2 times the sine of angle 2. All right, so let's do some problems with this. Just take your time as you're working through these. They're not hard. You just got to take your time. All right, it's not something that you can do as quickly as what we've been doing so far. All right, so here's an example. A light ray traveling through air is incident on a pool of water. If the light has an angle of incident of 30.6, what is the angle of refraction? So the biggest thing I would suggest with these is you need to draw a very basic picture. All right, draw your very basic picture. So here's gonna be my barrier, all right? And it says it's traveling through air. So this is the air. And it's incident on a pool of water. So water, all right? And so draw your normal. This is all you need to draw. This is the most that you need to be there, right? I don't have a big fancy drawing of a pool. Draw your line and separate it, all right? If the light has an angle of incidence, so it comes down here and it hits with an incidence angle of 30.6, all right? It wants to know what is the angle of refraction. So refracted light is down here. What is this angle? All right, so I have the sign. I'm looking for this sign, but what do I also need? I need my n values. Well, those are on your reference table. All right, so air, if you look, the n value for air, n equals 1, and the n value for water, n equals 1.33. All right, so now I have all the information. I have angle 1, I have N1 and N2, and I'm trying to find angle 2. So we're just gonna plug it in. Everything on this side goes together and everything on this side goes together. All right, so N1, 1 times, please be quiet. Thank you, it says office. So go over there and play, please, and be quiet. All right, N1 equaled 1, so 1 times the sine of angle 1, which is 30.6, all right, equals N2, which is 1.33, times the sine of angle 2, all right? All of you all did really well in algebra. That's why you're in physics. So from here, you should be good to go. So 1 times the sine of 30.6. So go ahead and type that half into your calculator. Please be quiet. 1 times the sine of 30.6 equals 0.51. All right, and that equals 1.33 sine of angle 2. All right, I need to solve for this angle right here. So that means I need to move everything else to the other side, right? So 1.33 and sine are being multiplied. So I'm going to divide by 1.33 so that I can move it by itself, 1.33. So I'm going to take that 0.51 and divide it by 1.33. And I get 0.38 equals the sine of angle 2. All right? I still need to solve for angle, which means I need to move the sine to the other side. Remember, what is the opposite of sine? How do I get that sine away? Inverse sine. All right? So now I make it sine to the -1 of 0.38 equals angle 2. All right? So I'm going to take second sine and I'm going to do 0.38. And that equals an angle of 22.3 degrees equals angle 2. That right there is your answer. That, if you were shining light into a pool at an angle, that is what angle the light was shining into the water. All right? So right here, that's angle 2, 22.3 degrees. All right? So that is how you use Snell's law. All right, let's do another example.
9.
Can you go get something out of my purse? Come here. Come get something out of my purse. Go get something for me. Bring me a piece of paper. All right, so let's look at one more example. Light is incident on a piece of glass in air. It's incident on the glass. That means it's hitting the glass. So down here is glass, all right? And up here is our air, all right? It hits at 31 degrees. So here's your normal. Remember I said that was very important. That's our normal. All right, and it hits that at 31 degrees. So right here is 31 degrees. If the index of refraction for the glass is 1.5, so N equals 1.5, what is the angle of refraction? So I'm looking for this angle, all right? So how can I figure this out? Air, we know that I need the N value. Where is that at? It's on my reference table. So N equals 1. So now we're just going to plug it in. Everything up top goes on one side and everything on the bottom goes on the other. So 1 times the sine of 31 equals into 1.5 times the sine of angle 2, which is what I'm trying to find. So,
Hey, Mommy.
hey, buddy.
Hey, Mommy.
Hey, buddy.
Hey, Mommy.
So 1 times the sine of 31 is 0.52, and that equals 1.5 sine angle 2. So notice all I did was I simplified my left side of my equation, all right? And then remember I need to move my 1.5 to the other side, so divide both sides by 1.5. So 0.52 divided by 1.5 is 0.347, all right, equals the sine of angle 2. All right, I'm trying to solve for the angle, so I need to move sine to the other side. All right, so what's the opposite of sine? Inverse sine. So that means I need to take the inverse sine of both sides. That's going to cancel this out, and I'm going to say sine to the -1 is 0.347. All right, and that equals my angle. All right, so second sine to the -1 of 0.347 equals, apparently somebody locked herself out, 20.3 degrees is the angle. So if you shine light onto that type of glass, it would shine off at an angle of 20.3. All right. Where did you go? Where did you go? You got stuck. Okay. So hopefully this helps make a lot more sense with the Snell's law and angles of refraction. Hey, buddy. Hey, buddy. All right. Let's do another example. Okay. What is the angle of incidence on an air to glass boundary? Air to glass. So air is up here, glass is down here. If the angle of refraction in the glass is 25 degrees. So it tells me it hits this angle at 25 degrees. And my glass index of refraction, it says is N equals 1.52. That was angle 2. All right, so now it's giving me my angle of, and I'm sorry, I wrote this in the wrong spot.
Hey, Mommy. Hey, Mommy. Hey, Mommy.
Hey, buddy.
Hey, Mommy.
It gave me the angle of refraction, right? Angle of refraction. That means it's telling me that this is my angle of refraction, 25 degrees. I want to know the angle of incidence. All right, so I need my n value for air, which we can look in our reference table, and n equals 1. All right, so now we're doing n.
Hey, mommy. Hey, mommy. Hey, mommy.
Hey, buddy.
Hey, mommy.
Hey, baby.
Hey, mommy. Hey, mommy.
So n equals 1. 1 times the, I don't have an angle here, so the sine of angle 1 equals n2, which was 1.52, times the sine of angle 2, which we found was, or we know is, 25 degrees. All right, so 1.52, we're going to simplify this side. 1.52 times the sine of 25 equals 0.64. So 1 sine angle. 1 times anything is what? The same thing. So guess what? I can erase this 1 right here. The sine of my angle equals 0.64. Well, I want the angle, so I need to get rid of sine by doing the inverse sine. All right, you want to wait until sine is the last thing left, then do your inverse sine. Sine -1 of 0.64, and that's going to give you your angle. Second sine to the -1 of 0.64. You should get to be, your angle equals 39.8 degrees. All right? So that is your angle of incidence. What is the angle of incidence? So you're looking for the initial one, and they gave you the second one. All right, so hopefully that makes a little bit more sense with Snell's law. I'll see if there's some more problems, and we can do some more examples. Oh, come back. All right, so you had the pre-lab worksheet. Let's see. Oh, so that was your Snell's law. Hopefully, there's no more examples. The only other thing, sometimes they'll give you both angles, which then it's 10 times easier because you don't have to do any inverse signs. You just solve it and find the n value. All right. So notice everything on the left I put on, or on the top I put on the left, and everything on the bottom I put on the right. All right. Do everything until you have nothing but sine of that angle left, and then do the inverse sine to find the angle. All right. So last part, let's look at calculating the index of refraction. All right. The index of refraction, so say I have a substance and I don't know the index of refraction, which can sometimes happen with like foreign substances, right? I'm going to calculate it using the velocity of light in a vacuum over how fast the light is traveling through that substance. So let's look up here. See, if you look at the first page of your reference table, let me see if I can see this in the screen. If you look at that first page there, all right, C value, it's right here, all right? 3E8 is the speed of light in a vacuum. So that's what you're always going to plug in for C when it asks you to find the index of refraction, all right? So the index of refraction, 3E8, all right? And that's what you're plugging in for C. That's your comparison to find the index of refraction. Let me in. So, the frequency of a wave is 5.1 E14 hertz. The speed of the wave in that medium is 2.1 E8. What is the index of refraction? So you're trying to find N.
Mommy, back.
Thank you. I'll take it back. Good girl. You're trying to find the index of refraction. So, all right, N equals C over V. Our C, we said, is always going to equal 3E8. And then I need the velocity. So guess what? They gave me some extra information. Do I care about frequency? No. That does not matter to me. I do not care about frequency. All I care about is the speed of it is 2.1 E8. Make sure you all are still using that E button. 2.1 E8, and that's going to give me my N value. So if you were to put this substance, whatever the substance is, on the reference table and list its index of refraction, you would put E8 1.42. This does not have a unit. Index of refraction is something that does not have a unit. I know we said all numbers have units except index of refraction. All right, there's no unit that goes with it. Hey, buddy. All right, so that's how you calculate the index of refraction. Let's look at another one. The speed of light in an unknown medium is measured to be 2.76 E8. What is the index of refraction? So it equals C over V. We know that C is 3E8. Forever and always, that is the speed of light in a vacuum. It's on your reference table. All right, 3E8 over V, which is 2.76 E8. All right, that's the number they gave me. So 3E8 divided by 2.76 E8. And your index of refraction is 1.09. All right? So that's how you solve for index of refraction. I believe that's the last one. One more. All right. And then this one's taken it another way, right? We have N equals C over V. It says they are composed of silica with an index of refraction of 1.44. That is our N. All right? How fast will it travel? We want to know the speed. All right? So now we're going to plug it in a little differently. We have N, which is 1.44. All right? And I know that C is always what? 3E8. So notice I just made my triangle out of these. All right? 3E8 divided by 1.44 equals a very, very, very fast number. Let's see. 2 point. Oh, let me convert it to. It'll be okay, buddy. Oh. All right. So if it didn't give it to you in scientific notation, you know how to go to second and then change it to scientific notation. All right. So 2.08 E8 is your speed. If it spit it out to you in the big number, it was 2.08333333. All right. So that is the same as this. Remember moving our decimals. 1, 2, 3, 4, 5, 6, 7, 8 times 2.08 E8. All right. So make that into a triangle if it's asking you for something else. So let's see. Is there anything we can? I wish there was another problem that we could look at to go over Snell's law. All right. I think you all will be good on this, but we can do one more just in case, and I'll go back and just do this one again. And because I want to just be able to show you all another practice in case you need some additional support. All right. So Snell's law, this is the one where it gives you the angle of incidence and it wants the angle of refraction, vice versa. All right. Light is incident on a piece of glass in air. So that means you have glass. Incident on the glass and it's in air. All right, at an angle of 31 degrees. That is your angle of incidence, angle 1. All right, if the index of refraction for the glass, which is N2 because it's on the bottom, right? So here's N2 equals 1.5. What is the angle that the refracted ray makes with the normal? All right, so here's my normal line. What angle did they give me? 31 degrees. So it hits this line at 31 degrees. All right, and it wants to know the angle that you make down here. All right, so what is the N value for air? It's in your packet, in your reference sheet. It is 1.00 or 1. All right, so you have 1, I'm going to plug it in, 1 times the sine of that angle, which is 31, equals N2, which is 1.5, sine of angle 2, which is what we're looking for. All right, so first let's simplify the left side. Simplify. So sine 31. Oh, let me put it in regular mode. 0.52. All right, that is this simplified equals 1.5 sine of angle 2. Remember, I need to get angle by itself right here. So I need to divide. These are being multiplied. The opposite of divide, multiply is divide. So 0.52 divided by 1.5 is 0.347 equals the sine of angle 2. How do I solve for angle? All right, I need to get angle by itself. So I need to take the inverse sine. Sine -1 of 0.347 equals angle 2. All right, so if I take the inverse sine of 0.347, I get 20.3 equals angle 2. All right, 20.3 degrees. So the degrees that it comes off right here, 20.3 degrees.
Mommy,
All right,
Mommy, poo-poo.
you gonna go potty?
Poo-poo, Mommy.
Gonna go potty?
Poo-poo.
All right, come here, we're done. Can you wave goodbye? Come here. Wave goodbye. Say bye-bye. Say Merry Christmas. They're about to go on Christmas break. They have to take a test first. What do you think? Yeah? Say bye-bye. Can you blow them kisses? Mwah. Mwah. There you go. All right, say bye-bye.
Bye.
All right, let me know if y'all need anything. Leave comments on the videos if that will help you, and I'll try and go on and respond to them. Also, you all have my phone number, so feel free to reach out. If you get stuck on a problem on your review or on your packet and you're not sure how to do it, then just take a picture of it, send it to me, and say, hey, Miss Simmons, I need some help, and I'll do what I can to help you. Hopefully, you all have been getting along very well. I heard that y'all are doing an awesome job, and that y'all have still been working really hard. So I'm so proud of you. I cannot stress that enough. I've been thinking of each of you.